Hello, so in this video we are going to be talking a little bit more about homogeneous systems. We're kind of at the very end of homogeneous systems. We kind of got everything that we can out of homogeneous linear systems, okay? Remember that homogeneous linear systems, we have a system that looks like this. There's no constant on the end. That's all that homogeneous means, okay? So there's no plus k. And of course we can collapse this system down into something which looks like this, okay? So this is homogeneous. We've talked about this before. And yeah, we kind of at the very, very end, basically what we're going to do in this video is just kind of introduce some new matrices, some new ideas that can kind of then bring us back to non-homogeneous cases. Because the last kind of couple of videos, I suppose, are going to be on, or a couple of subjects, don't know how many videos there'll be, but last couple of subjects that we're going to cover are the non-homogeneous cases, okay, of these solutions. So kind of, we can get a lot of information about out of the homogeneous case, and we can kind of get 90% of the information that we need just by considering a non-homogeneous case, a set of solutions or a system as a homogeneous system. So we can get kind of 90% of the information that we need. But that last little 10% we need to convert back to the non-homogeneous system. All right, and yeah, and so kind of we're going to use this video to just kind of set up the ideas that we need in order to move back to the non-homogeneous case. Hopefully that makes a bit of sense. So the first type of matrix that I'm going to be talking about in this video is something called the fundamental matrix. Now, if you remember, I've talked about fundamental solutions before. So yeah, a matrix is just a table, okay, and it makes sense that it will just be a table of fundamental solutions. Right. Now, I've talked about fundamental solutions before. If you remember, we get a solution. We get a solution out of this system, okay? And let's say this, we get a solution, say, for x1. So x1 will look something like this. So it'll be the eigenvector u1, and the eigenvector will come from A, okay, which is of course the matrix of coefficients, okay? So we'll have u1, which is the eigenvector, e to the eigenvalue, which is, of course, again, comes from A, the matrix of coefficients, times t. Okay, so this is what my solution should look something like for x1, say. And it'll be exactly the same kind of thing for x2. So it'll be eigenvector, the second eigenvector, e to the second eigenvalue. Okay, and so on and so on and so on for all of our n different solutions. So now, basically, if I, and you can verify that by differentiating with respect to t, I can get this system out and such like. So yeah, this is basically my fundamental solution is going to look like. And if you remember, what's the difference between a fundamental solution and a solution? Well, a solution is just exactly that. It can be anything, okay? But a fundamental solution means it cannot be broken down any further. So in other words, I'll have a sort of a series of, a list of fundamental solutions, or a list of solutions, sorry. And if it's fundamental, it basically means that one of those solutions cannot be, all of those solutions cannot be broken down any further, or more specifically, one of those solutions cannot be written in terms of any of the other solutions. So in other words, we give that a special name. It's called linearly independent. Yeah, it's in other words, say like, okay, a slightly contrived example that's not specific here, but let's say I have 4t as a solution, for example. Obviously, I've just said that my solution will look something like this or like this, okay, with the eigenvectors and eigenvalues. But let's say, for example, just to kind of for the sake of clarity, let's say I have a solution 4t, all right, and a solution 2t. So these are my two solutions, okay. Well, fairly obviously, this would be linearly dependent, not linearly independent. Why? Because I can break 4t down in terms of 2t. 4t is equal to, well, it's 2 times 2t, yeah? 2 times 2t. So in other words, I can write one of the solutions in terms of the other solution. Okay. And, okay, again, perhaps a slightly contrived example. An example of non-linear, linearly independent would be, say, if I had a solution cos t and 4t. I can't write 4t in terms of cos t, and I can't write 2t in terms of 4t. So again, slightly contrived, but for the sake of clarity, hopefully that makes a little bit of sense about why, what linearly independent means, because that's kind of really crucial to understanding what a fundamental matrix is. So okay, let's say this is a fundamental solution. x1, x2, right the way through to xn are all fundamental solutions, so they cannot be broken down any further. They cannot be written in terms of any of the other solutions. All right, then I could just write them as a matrix. So let's say I have x1, x2, x3, right the way through to xn, right? And I can just write that as a matrix. right? So I just write those solutions as a matrix. I'll give you an example in a little while to show you why it's a matrix and not a vector. And the clue is because you've got an eigenvector going on here. And just so you're effectively multiplying this e to the lambda t by this vector. Okay, so you'll end up with a sort of a list of vectors, if you like. Okay, so it will just be columns. Right. And the notation we give for fundamental matrix is psi. And of course, psi will be dependent on t because all of our solutions will be dependent on t. You know, this solution x1, has a t in there. Yeah. Okay. So it will be dependent on t. Now, of course, because they're linearly independent, or because, you know, all these solutions are linearly independent, then that means that, of course, we introduced this idea of the Vronskin in one of the videos. The Vronskin is just a determinant of this fundamental of this matrix of fundamental solutions. Yeah. So the matrix of the fundamental solutions. So it's just a determinant of this. So determinant of this matrix here, and of course, because all these solutions are fundamental, it means they're linearly independent. And I showed you in one of the videos that, or in one of my previous videos, that the determinant has to be non-zero because it's linearly independent. Because if it's linearly dependent, basically we get cancellations. So because it's linearly independent, none of the solutions can be written as any of the other solutions. So therefore, there's no cancellations which occur. Okay, so what does this mean? If a determinant is non-zero, that means that it is, what is it? It's singular. Okay? No, non-singular, sorry. I confused myself then. It's non-singular. Okay, in other words, there's an inverse that exists. Yeah, so inverse exists. Yeah, if it was equal to 0, then it's singular, and therefore there's no inverse. But because it's not equal to 0, it's non-singular, and so therefore an inverse must exist. And we're going to come on to that and use that fact in just in a little while. Okay, so basically what we've got is now we've got a matrix. Okay, so this is our matrix up here. I'll show you kind of with an example what that would look like. So because this is a matrix. Okay, and this matrix consists of solutions of our original equation. So what is our original equation? dx by dt equals ax. Okay, this matrix represents all of the fundamental solutions that satisfy that. Then fairly obviously, are you happy that then x can just be written as this fundamental matrix? So in other words, this fundamental matrix will satisfy this equation. So in other words, we'll have d phi by dt will just be equal to a times phi. Okay. Why does that make sense? Well, let me just give you perhaps a slightly trivial example. Let's say, for example, we have an equation that looks like this. So 6 equals 4x squared plus 2. All right. Well, what are the solutions to this? The solutions to this are 1 and minus 1. Yeah, so x equals 1 and minus 1. Well, then, fairly obviously, if we just replace 1 or minus 1 back into this equation for x, we're still going to get that will still satisfy the solution. So, we can put 1 or minus 1 back in there. It will still be true. This equation will still be true. This equality will still be satisfied. Okay, so I can write it as 6 equals 4 times 1 squared plus 2. Yeah, that is still true. Or equally, I could write it as minus 1. It doesn't matter. The point is that I can now substitute my solution. If I substitute my solutions back into my original equation, it's still true because fairly obviously the solutions satisfy the equation. So that's why I can write this. Okay, I can have d phi by dt equals a times phi. Yeah? Okay. So hopefully that makes a bit of sense. Okay, so now I'm just going to show you kind of a fairly simple example with a 2 by 2 matrix. So let's say, for example, we have dx by dt. Just show you how to form the fundamental solution. Hopefully this will make a little bit more sense now. This is dx by dt equals, let's say, 1, 1, 4, 1 times x. Okay, where x is just, let's say x is just our variables x and y. All right. So basically what I want to do is I want to try and form the fundamental matrix based on this system. Okay. Well, the way to do it is basically the first thing which I need is an eigenvectors and eigenvalues. So let's say I have eigenvalues. Well, I know the eigenvalues. I worked it out earlier, but you can do it yourself if you want to, just for practice. But the eigenvalues of this matrix are 3 and minus 1. and minus 1. And the eigenvectors, let's say u1, corresponding to lambda 1, so the eigenvector corresponding to, our eigenvalue being 3 is 1, 2. I worked that out earlier. You can, again, it would be good exercise for you to be able to work it out yourself. And the other eigenvector corresponding to lambda 2 equals minus 1 is 1 minus 2. Okay, so these are now my two, these are my eigenvectors and eigenvalue solutions based on this matrix. Okay, so what would the fundamental solutions be? Remember, I'm looking for it on the form of u e to the lambda t. Yeah, so this is what my fundamental solutions would look like. So my variables are x and y, so I'll have x will equal and y will equal. That's what I'm after. That's my solutions. Okay, I'm after what x equals and what y equals. Well, x will equal my first eigenvector, so u1, e to my first eigenvalue, lambda 1t, and likewise for y, it will equal my second eigenvector, my second eigenvalue. Alright, so let's have a look and see what this is. So this is 1, 2, e to the 3t, and this is 1 minus 2, e to the minus t. Yeah? Okay, so now when I form a fundamental matrix of this, my fundamental matrix, phi of t, will be this x and this y. So my fundamental solutions of this. So what will it be? It will be 1, 2. Yeah, it'll be 1, 2, e to the 3t. And it'll be 1 minus 2, e to the minus t. Okay, so just replacing that. And then if I just expand this out, I end up with e to the 3t, that's e to the 3t, and this is 2e to the 3t in this element here. And then this would be e to the minus t, and here I'll have minus 2e to the minus t. So in other words, this is my fundamental matrix here. Okay, just based on that. So hopefully you can see now how you can form a fundamental matrix just based on some fundamental solutions. Okay. Okay. So hopefully you're happy now a little bit with fundamental solutions and fundamental matrices, and that kind of makes more sense now. Now just recall that if we have, our system, like we had at the beginning of the video, let's just try and find it. Here's our system, okay? Well, we can have a general solution, which will just be a linear combination of all of our solutions. You know, x1 equals, x2 equals, it'll be our solutions, and so if it's just a linear combination, let me just write it down just to show you. Okay, so we'll have, let's say we have solutions x1, x2, right the way through to xn. Alright, well our general solution will be these, these solutions added together, right the way through to xn. Okay, but we can have any multiple of these solutions, because if we multiply it by a number, it will still be a solution. Okay, multiplying by a number doesn't make a blind bit of difference, because if you remember, it's based on eigenvectors and eigenvalues. Our solution's based on eigenvectors and eigenvalues. Okay, well, just multiplying it by a number will just basically extend this eigenvector and eigenvalue. But this eigenvector already goes to infinity anyway. Okay, so just multiplying it by a number won't make a blind bit of difference. Okay, so we can have any multiple of our solutions as well included, and this is what's known as a linear combination, because it's a combination of our solutions arranged in a linear way. Okay, well, let's assume that I've got all the fundamental solutions in this matrix. Okay, so in other words, every single solution cannot be broken down any further. Every single solution can be written totally independently of any other solution. Okay, so I'm assuming that all my solutions are fundamental, so therefore I can form my fundamental matrix, yeah, x1, x2, right the way through to xn. Alright. Well, look, this isn't... Well, look, I can basically use this fundamental matrix to get back, use my fundamental matrix to get back to my general solution. How? Just by multiplying it by a constant vector. Let's say a constant vector, my constant vector is called c, and it just consists of c1, c2, right the way through to cn, so all of my coefficients. Okay, all of my constant coefficients in my linear combination. So this is what I'm trying to get back. Okay. Well, then if I multiply this by this constant vector by my my fundamental matrix, so I do gamma times c, phi times c. Okay, can you see that when I multiply it out, so I'll have something like x1, x2, xn And then here I'll have C1, C2, right the way through to Cn. Okay. When I multiply this out, I'll have this is equal to C1 x1 plus C2 x2 plus, and I'll keep going, right the way through to Cn xn. Well, that's what I started with. That is my linear combination. Yeah? So in other words, this is what x is equal to. X can be written, the general solution of x can be written as phi times my constant vector. Okay, so this is now a solution. I've now got a solution. Basically, you know, this is what my video is all about. I'm just trying to kind of form these kind of ideas that we've built up until now in kind of a nice, neat little vector matrix notation. So in other words, what I've written now is I've written my general solution, my linear combination, as in terms of vectors and matrices. Okay, so that's going to be really useful for kind of where I want to go now. All right. So next thing I want to talk about is an initial value problem. Now remember, initial value problem is you get given a set of initial solutions. Okay, so in general you can have an infinite or loads and loads of different, at least loads and loads of different solutions. All right, and so be given some initial data just determines which solution you want. So you'll have, you know, say like 300,000 solutions. Being given some initial data just allows you to narrow the search down even further to what solution you want. And quite a lot of the time it actually pinpoints the exact solution, which you need. So let's say, you know, we have our system, dx by dt equals ax, again, homogeneous. Okay, and we get given some initial data. So let's get given that our solution, or our value, you know, our solution, our x vector at some time 0, because of course this is dependent on time. So at some time 0, that will be given by some value. Let's call it x0. And it'll be a vector, okay, fairly obviously, because it'll be x1 at that time value, x2 at that time value, x3 at that time value, which of course we can just write as this. Okay, this is just notation. This is what it means. It's just some initial vector. All right, so this is what, you know, what's going on. Well, we've just shown that we can write the solution to this as phi times c. So x equals phi times c. Okay, and as you can see, this will clearly be dependent on time since it contains our fundamental solutions, which are constant. Okay, which contain t. Yeah, so as you can see, this will clearly depend on time. Yeah, or this matrix here, I should say, will depend on time because it contains, you know, our fundamental matrix will contain our fundamental solutions, which all our fundamental solutions depend on time. You know, I've just shown what our fundamental solutions look like. It looks like E1, U1, e to the lambda 1t. Yeah, so clearly there's a t involved in our fundamental matrix. So our fundamental matrix will depend on time as well. Okay. So basically how I should write it is I'm going to now include dependencies. Up to now, I've admitted the dependencies of which everything's on. Our constant vector won't be dependent on time. Our x will be, you know, our x solution will be dependent on time. Yeah. Our fundamental matrix will also be dependent on time. But our constant vector won't be dependent on time. It'll just remain constant through time. Okay. Well, I've been given the initial data that at time 0, I have x0. Okay, I have x0. So if I just now evaluate my solution at time 0, so just replace t by time 0, I'll have this thing going on. This is just introducing notation now. Okay, so I'll just have this thing going on. All right. Well, let's do a little bit of rearranging. And of course, that thing is equal to, because x0 is equal to x at time 0, then that thing will also be, you know, this phi of time 0 times our constant vector will be equal to x0. Okay, just kind of introducing the notation now. So hopefully you're following so now. There's nothing difficult going on. All I'm just doing is just introducing the notation. Perhaps I'm sort of making it overly complicated. Okay. So let's use this thing. I'll just write it out again. So phi at time 0 times c equals x0. Okay, so I've got this. All right, but now I want an expression for t. That's what. Sorry, for c. That's exactly what I'm trying to get. I'm trying to work out what this constant vector is. Because up until now, I've said, well, okay, our general solution can have constants in it, but I want to now work out what that constant vector actually is. Okay, and so what I now need to do, as you can clearly see, I need to move this phi of times 0 onto the other side. Well, remember that I said before. That our fundamental matrix phi of t, okay, is made up of fundamental solutions. So therefore, it's linearly independent because all our solutions cannot be written as any of the other solutions, okay, which means that all of those solutions are linearly independent. So therefore, our matrix, which is just a table of all those solutions, will also be linearly independent. So therefore, if it's linearly independent, remember that Vronskin is the determinant of this thing. So the determinant of this thing, okay, cannot be equal to 0. So therefore, phi inverse exists. So kind of a lot of argument, but it kind of makes sense if you think about it. It just means that there is an inverse of this fundamental matrix which exists, which means that I can take this phi over to the other side. So in other words, I can write now C as phi inverse of t naught times x naught. All right. Okay, so I've got this now. This is what C is. So therefore, if I plug back, C back into, where do I want to plug it back into? I want to plug it back into here to find out what x of t is. Now I know what C is. I've got an expression for C. Yeah, this is my expression for C. I want to now plug it back into here. It's x of t equals phi of t times C to basically get a general expression for x of t. So x of t is equal to phi of t times C. Well, what's C? C is given by this. We've just worked out what C is. So it's phi inverse of t naught times x naught. All right? Okay, good. So we've got this basically now. So this is now our general solution. So maybe if I unbox things. This is now our general solution. Okay. Basically based on a fundamental matrix. Right, well, cool. So basically, I know I have talked about this before, but I think I didn't make it really that clear. So I'll talk about it again. Basically, because we've got our fundamental solutions and they're all linear independent, the geometric meaning of that means that they all lie in their own individual plane, or they all lie in their own individual axes. So if they're linear independent, it basically means that they cannot be broken up into into parts of the other one. So the only way that can happen is if they're all perpendicular to each other. So they all lie in their own individual plane. So this vector here lies, this is say x1, this is x2, and this is x3. So this solution lies in, say, the forward and backwards plane. This solution, x2, lies in the left and right plane, and x3 lies in the up and down plane, for example. So basically, we can write that for some value of t naught, we will get the basis vectors out. Yeah, because our fundamental solutions are linearly independent, which means that we've got this thing going on. The only way that, the geometric application of that is that they all lie in their own individual plane. Maybe I should write out what, x1 is. So x1 is 1, 0, 0. Yeah, because it's the unit vector in the x1 direction. X2 is 0, 1, 0, because it's the unit vector in the y direction. And x3 is the unit vector 0, 0, 1, which is the unit vector in the z direction, the up and down direction. Okay, and these are what's known as basis vectors. They're basically unit vectors in the relevant direction. Okay, so that for some value of t naught, we will get the x1 evaluated at t naught. So our first fundamental solution evaluated at a particular value, okay, will be given by the first basis vector, which of course is the first element just being 1, and all the other elements being 0. Okay, and likewise for x2 at some particular value, we'll get the second basis vector. So that's u. So that's the second element being 1. Okay, and likewise for x3, we'll get the third element being 1, right the way through to xn. Particular value is given by en, which of course is just the last element being 1. Okay, so hopefully this kind of makes sense. Well, let's just say then, let's just say then, so we've got now x1 at some particular value will be given as this basis vector, so the first basis vector. The second solution at the same particular value will be given by the second basis vector. So what I'm basically saying is that for some value, when I plug it in, I get the basis vectors out. So when I put some value, some particular value, t0 into my fundamental solutions, I get the basis vectors out because they're fundamental, so therefore they're linearly independent. So for some value, I basically get the unit vectors in the corresponding direction because they're linearly independent. Okay, so if I now form x1 of t0, if I form, a matrix of all these fundamental solutions, fairly obviously what it will look like is something like this. So 1, 0, 0, right the way through to 0. This will be 0, 1, 0, right the way through to 0. So this is x2 now. This is x3, 0, 0, 1, 0. And then this one right the way through to xn, which is 0, 0, 0, right the way through to 1 at the last one. So can you see that what I will get is the identity matrix? Because basically these solutions will be the evaluated T0 get the basis vectors out. Well, when I put them all together in my fundamental matrix, because each of these fundamental solutions correspond to the basis vectors, when I put them all together in my fundamental matrix, I get the identity matrix out. So what I'm going to do is I'm going to give that a special name. It is a fundamental matrix, but I'm going to give it a special name to show you, or to show that, I get the basis vectors out for that particular time value. And I'm going to call that phi. Okay, so phi of t is going to be given by the identity matrix for that corresponding dimension. Okay, so therefore, if we kind of put this into context, we have our initial value problem. So we have our initial value problem. So again, I'm just summarising what we've got up to now. Basically, I'm just trying to collect the ideas together. So our solution at some time value, t0, will be given by x0. Okay, and we have just worked out the solution just a minute ago, that our general solution will be given by our fundamental, in terms of a fundamental matrix. So phi of t, phi inverse of t0, okay, times x0, so our value at x0. So basically, this is our fundamental solution based on some initial conditions in our fundamental matrix. Okay, and also I've shown you that phi at some time value t0 will be given by I. And notice as well, because phi at time 0 will be equal to the identity matrix, fairly obviously the inverse of phi, and there will be an inverse which exists because it consists of linearly independent solutions, so therefore the determinant is non-zero. Okay, the inverse of that fundamental matrix, that consisting of the basis vectors, will also be equal to I. Okay, so now if I just replace, because of course phi is just a special case, of the fundamental matrix. Okay, it's just, phi is a fundamental matrix, so this phi here is a fundamental matrix, but it's a fundamental matrix, but it's with the basis vectors. Okay, so now if I just replace the two, so I end up with x equals phi of t times, inverse of t0 times x0. Okay, so basically what I've just done is replace these two. I've just replaced these two. Right? Hopefully you can see that. So now, if I use this fact that this evaluated at time 0 is just the identity matrix, therefore I end up with phi of t. Well, the identity matrix just corresponds to 1 in kind of the matrix world. Phi of t times x0. Okay, so here's my final solution. I end up with x equals phi evaluated at t times x0. Sorry, times x0. Yeah? So now we can say that for any, because we now got an expression, we can now say that for any fundamental matrix, okay, we can now say that because x equals this, times t0, x0, and because as well, we've just shown it's equal to this thing here as well. It's equal to phi of t x0. And so now, basically, I can sort of do a little bit of cancellation. Those two vectors can cancel if I just multiply by the inverse. Okay, and so now what I'm left with is that this is equal to this inverse of t naught. This is just algebra. Okay, I've kind of taken you through the algebra. It's not difficult. Do the algebra yourself, and you think, oh, okay, this isn't that difficult. It's just I know how it feels that when you do a lot of algebra yourself, or when you sort of get, I'm presenting a lot of algebra, it kind of seems harder than it is, but it's really not. You do the algebra yourself, it's really not that difficult whatsoever. So basically, what I'm saying is that when the fundamental matrix is considered as this, which of course is the fundamental matrix consisting of the the basis vectors. All right. When I've got the basis vectors, sort of fundamental solutions, and that's what this is equal to now. Okay. So in other words, if I just put in a value to get the fundamental basis solutions out, then that's what it will be equal to. This right hand side. Okay. It'll just be equal to my fundamental matrix times the inverse of my fundamental matrix evaluated at my particular time value. Okay, so in other words, okay, let's go back to the general solution of the initial value problem. So I've got x equals this times inverse of t naught, x naught. Okay, well that now, because this is equal to I, that now is equal to I, I'm just left with this. If I put it all back together, that's what it's equal to. Okay, now why is that useful? Why is that useful? So basically what I've done is, all I've done to get to this step is I've just used this, plugged it back into my original value, okay, because this is what it's equal to. So this is what I end up with. So why is that useful? Well, because we know what this is. We know what this is. Okay. So basically, if you're solving a system that can start in many different states, in other words, you can have many different initial conditions. In other words, it can start in lots of different initial values, so it can start from many different initial states, initial positions, lots of different values. Then basically, once you've got this phi of t, you can find any solution to any initial condition just by using this fact. Just by using this fact that basically, if you can find this matrix here, this fundamental matrix here, then essentially, what is this matrix here? Well, it's just a transformation of the initial conditions. So in other words, these are maybe I'm not explaining this. This matrix here, I'll start again. This matrix here is my fundamental matrix consisting of my basis vectors. So if I can find that matrix, okay, and this of course is just this x naught is just my initial value, my initial conditions, so my initial solution, my solution evaluated at my initial conditions. Okay, so basically what this does is it transforms some initial conditions into my solution. This is what this phi of t matrix does. It transforms some initial conditions, which are given by x naught, into my solution. So in other words, I don't even have to kind of do anything more than that. I just have to be given some initial conditions, and providing I know this matrix in the middle, this fundamental matrix in the middle, I can automatically just transform it into my fundamental solutions. Okay, so that's really, really useful. Okay, so fine. We've got this kind of idea. So what is this function, what is this fundamental matrix going to look like? Okay. Well, in order to answer that question, what I want you to do, so basically, up to now, if you didn't sort of get where this comes from, do the kind of calculations yourself. Fine, you could use mine as a kind of basis, but I really encourage you to do the calculations yourself to kind of see where all this comes from. Okay, so what I want you to do is I want you to consider the scalar case. So in other words, let's just consider this scalar case, dx by dt equals ax, okay, given some initial conditions, so x at t0 equals 0, so time equals 0, and let's call that x naught. So that's the scalar case. Yeah. Then let's consider the matrix case as well. So the matrix case is similar to this. This is just what we've been considering up to now. The matrix case, okay, is equal to ax, okay, and again given some initial conditions. All right, except now this is a vector instead of just a value. Okay, so basically, hopefully you can see the similarities between the scalar case and the matrix case. Yeah, it's now instead of just a number or a variable, it's now vectors and matrices going on. All right, so let's try and solve this scalar case. This is just an ordinary differential equation, nice and easy to solve, hopefully, if you know your techniques. Okay, and I'm going to do it by this way. So I'm going to integrate both sides. So I'm going to have 1 over x dx equals integration of a dtt. Again, all I'm just doing here is I'm just considering this dx by dt as a fraction. Okay, I'm getting everything involving x onto the left-hand side and everything involving involving t, or a constant in this case, on the right-hand side, so a. Okay, and this is what I end up with, and just integrating now both sides. Okay, so now if I integrate both sides, I'll end up with natural logarithm of x equals at plus some constant of integration. Okay, and I can now write x is equal to e to the at plus c, which of course is just equal to, let's call it a, well no, let's not call it a, let's call it capital C, e to the at, and there we go. Okay, so this is what x is now equal to, it's c e to the at. Alright, now if I use my initial conditions that x at time 0 is equal to x naught, okay, so in other words, x at time 0, so what's that? I just put 0 into for t, so I'll get c e to the 0, which is just c, and that's equal to x naught. So in other words, I end up with c is equal to x naught. So now I can say, so I've got a value for c now, okay, it's just x naught. So now I can say that x is just c e to the at, where c is just x naught, e to the at, okay? So now this is my solution, okay? Well, if I've just shown that if I solve the matrix case, so this is the solution to the scalar case. Okay. If I solve the matrix case, my solution is, I've just shown it's phi x naught. Okay, where these are both vectors now. So this is my scalar case up here, and this is my matrix case here. Yeah? Okay. So hopefully you can see the similarities. You know, we had the similarities, of course, with the original equations, where, you know, we just scaled it up into a matrix or a vector, corresponding matrix or vector. Now hopefully you can see the similarities. So look, we've got an x here, and we've got an x here. This is just a vector, and this is just a scalar function. That's fine. Okay. Again, we've got an x naught here and an x naught here. So it makes sense then that the e to the at is gonna, or the phi is gonna follow the form of e to the at then, because hopefully you can see the similarities. That's the only thing that's left. You know, we've paired all the other things off. So the thing which is left is e to the at and phi. So in other words, phi is going to look something like e to the at. In actual fact, it can be shown that that is the case. It can be shown that phi is actually equal to e to the, well, it's no longer a scalar. It's now it's just a matrix. Okay, so whereas you can hopefully see that a here, the scalar a here corresponds to, you know, compared to the matrix a here. All right. So now this is just going to be e to the at. So this is what phi is actually equal to, and it can be shown that that is the case. We can also expand that out. So yeah, this is the general solution given some initial conditions. Okay, we can also expand this out. So what's e to the x? You know, what's the power series for e to the x? Well, it's the sum of well, you can see it actually from 1 plus 1 plus x squared over 2 plus, or factorial I should say, plus x cubed over 3 factorial plus so on, so on, so on, which of course is just equal to the sum of x to the n over n factorial from n equals 0 to infinity. So therefore, what is e to the at going to look like? Well, we're just basically replacing x by at now, so it'll just be the sum from n equals 0 to infinity of at to the power n over n factorial. Well, now if I just expand this this n to the power n out, it's just going to be that. Okay. Well, what happens if we put n equals 0 into this? If we put n equals 0 into this, we're just going to get the identity matrix out. So when n equals 0, we get the identity matrix out. So therefore, I can sort of expand a bit of this power series into looking something like this. From n from 1 to infinity is just a n t to the power of n over n factorial. Okay, this is just what AT looks like, and that's the general form of phi. Okay, so our fundamental matrix is going to look something like that.